This question is from GATE Mechanical Engineering of 2012. This is question number 41. The question is, water whose specific heat at constant pressure is 4.18 kilojoule per kilogram Kelvin at 80 degrees Celsius enters a counterflow heat exchanger with a mass flow rate of 0.5 kilogram per second. Air whose specific heat capacity at constant pressure is 1 kilojoule per kilogram Kelvin enters at 30 degrees Celsius with a mass flow rate of 2.09 kilogram per second. If the effectiveness of the heat exchanger is 0.8, the LMTD, that is the logarithmic mean temperature difference in degrees Celsius is. So we need to find the LMTD of this counterflow heat exchanger. So in case of counterflow heat exchanger, we know that heat capacity of hot fluid is given by MHCH, that is 0.5 times into the specific heat capacity of hot fluid, that is 4.18. This will be equal to 2.09 watt per Kelvin. Now for the cold fluid, we can calculate the same. MCCC, that will be equal to 2.09 into 1. The value is given in the problem. That will be equal to 2.09 watt per Kelvin. Now since we know here that CH is equal to CC, that is heat capacity of hot fluid is equal to heat capacity of cold fluid, whose value is 2.09 watt per Kelvin. That means the heat exchanger is balanced. Okay, so let's write here balanced heat exchanger. Okay. Now before going further, let's see the diagram of temperature along the heat exchanger. In y-axis we represent the temperature, and along x-axis we represent the length of heat exchanger, let's say x. Okay, so let's say the heat exchanger is of some length L. Okay, now the hot fluid, the temperature of hot fluid will decrease, right? So TH1 and this is TH2. Cold fluid will be passed in the opposite direction, right? So the temperature of cold fluid will increase, TC1 inlet, TC2, right? Now the effectiveness of balanced heat exchanger is given by TH1 minus TH2 divided by TH1 minus TC1. The value is given 0.8 effectiveness, which is equal to 80 minus TH2 upon 80 minus 30. These values are again given in the problem. So from here we can find the exit temperature of hot fluid, that is equal to 40 degrees Celsius. Okay. Now to find the exit temperature of cold fluid, so from energy equation what we can write, MHCH multiplied by temperature difference TH1 minus TH2 will be equal to MCCC multiplied by TC2 minus TC1. That means the heat emitted by hot fluid is equal to the energy gained by the cold fluid. Okay, so now let's just substitute the values. All the values are given in the problem. 0.5 multiplied by 4.18. Now TH1 is 80. We found TH2, which is 40. This is equal to this is 1 multiplied by 2.09. TC2, the value we need to find out, minus 30 degree. Okay, so from here if we solve this, we'll get the temperature of cold fluid at exit will be 70 degrees Celsius. Okay. Now the temperature difference delta T1 will be equal to TH1 minus TC2, that will be equal to 80 minus 70. The temperature difference here TH1, this delta T1, here it is delta T2. Now let's find out delta T2. So delta T2 will be equal to TH2 minus TC2, which will be equal to 40 minus 30. So this value is also 10 and this value is also 10 degrees Celsius. Okay, both are 10 degrees Celsius. That means in a counterflow heat exchanger, if delta T1, let's write, if delta T1 is equal to delta T2, then using L'Hopital's rule, we can write this delta T1 is equal to delta T2, which is equal to LMTD. So LMTD is equal to 10 degrees Celsius. Okay. So the correct option is option C. For more information on counterflow heat exchanger and LMTD, the logarithmic mean temperature difference, you can refer to NPTEL course lecture number 60, Heat Exchangers 1 on Conduction and Convection Heat Transfer by Professor S.K. Som of IIT Kharagpur.